I am Michele Garau, and I am a postdoctor at NTNU at the Department of Information Security and Communication Technologies. And in this presentation, I will present part of my research during these 2 years of postdoctoral research, which focuses on 5G communication for smart grid application, which is also part of the project CINELDI. So this is the outline of my presentation. First of all, I will make a short excursus over the evolution of cellular communication towards 5G, and then I will describe the main technologies that enable this transition towards 5G in more details. And then I will make some examples of different service slicing in the smart grid context. And finally, in the last part of the presentation, I will talk a little about different issues related to the risk and reliability in complex systems, more specifically in the domain of smart grid. So first of all, what is 5G? 5G is essentially the last generation of mobile communication technologies, which is a technology that dates back in the early 80s, when the first generation of this technology was established essentially for allowing voice communication between mobile devices. Then, starting from the second generation, there has been the first transition from an analog signal to a digital signal. And along with voice communication, we had the first examples of data communication, more particularly in this case, we are talking about the text messages. Then, starting from the third up to the fourth generation, the relevance of data communication has become more and more increasing compared with voice communication. So the main driving force in the evolution of this technology has been essentially to allow higher volumes of data transmission through wireless mobile communication. And then the 5G essentially goes into the same direction. We can see how, compared with the fourth generation, it is expected to have higher data volumes, higher densities of connected devices to the same cell, lower latencies, and finally better performances in terms of energy consumption for battery-powered devices. But I would like to show how 5G is not just better performances, a version of LTE with just better performances, but it implies a paradigm shift compared with the older mobile communication technologies. What is the so-called 5G roadmap? So what are the main directions in the development of this technology? We can identify essentially two directions that, of course, are interworking between each other. The first one, which is called LTE 5G in this diagram, essentially focuses on enhancing the mobile core of LTE. So an evolution of the LTE core network in order to support as many use cases as possible. And I will go back to the concept of use case soon. The second one, NR5G, which stands for New Radio 5G, focuses on the development of a new radio interface that exploits the higher frequencies in order to achieve higher throughput and shorter latencies. So I have briefly talked about use cases. What are the use cases that are expected to be part of the 5G communication? Typically, they are classified into three main categories. enhanced mobile broadband, mission critical services, and massive Internet of Things. The first category, enhanced mobile broadband, it is essentially addressing the traditional usage that we have experienced until now with the LTE. So to be able to provide extreme capacity and high data rates for data transmission to and well, for mobile devices, essentially smartphones, laptops, and tablets. So in this case, the most demanding applications can be listed with video streaming, essentially, also, but also virtual reality and augmented reality, which it is expected to increase the data traffic significantly. And so in this case, the main requirements are in terms of high data rate capacity and density in the connection to the single cell. So this is something that we somehow have already experienced with LTE, but we can observe that there are two use cases that are quite new for this technology. For example, mission critical services, which addresses essentially industrial communication. For example, the communication that will support the autonomous driving of electric vehicles, control of robotics in industrial context, also the e-health. And you can understand that in this case, the requirements are completely different compared with the previous case. For example, the high reliability and the extremely low latency are very important in this scenario. And of course, the security of the communication system. And finally, the massive Internet of Things. In this case, we are talking about those small devices that it is expected will be part of our daily life in the near future. For example, wearable devices, and also all the set of sensors that it is expected will be part of our homes for domotic applications and smart cities, also smart farming. In this case, it is important to have a very low energy consumption, since many of these devices will be powered by battery. High density, since it is expected that in a square kilometer there will be thousands and thousands of these devices, and also deep coverage, both outdoor and indoor. And as you can see in this diagram in the right upper right part of the slide, it is possible to visually appreciate how all these use cases are completely different in terms of requirements. And so you can understand how the 5G is expected to be very flexible in order to address all these specific requirements in the same physical infrastructure. So what are the technologies that enable this transition towards 5G? Essentially, the directions can be classified into two concepts that are the softwareization and the virtualization. And I will explain these concepts in the following slides. The main idea is essentially to exploit the same physical infrastructure by creating many virtual networks which address specific use cases, as we have seen before, and that are reciprocally isolated. So we are moving from a communication infrastructure as a monolithic platform to a flexible service delivery platform. In fact, it is often said that the 5G is more than technology-oriented, service-oriented. It is oriented to provide a specific service, more than just a generic communication. So the first concept is, as I said, softwareization. well, SDN stands for software-defined networking. The main idea is given a generic device of the traditional communication network, like for example a router, which is traditionally divided into two layers, data plane and control plane, where the control plane is the logic of the device. Meanwhile, the data plane is essentially the hardware. To move the control plane, so the logic, up to a control center. So shifting from a distributed approach to a more centralized approach. What are the benefits into this transition? Essentially to have a higher flexibility, since changing the behavior of the network in this case means just updating a specific software. So it is possible with a centralized control to dynamically change the behavior of the network, for example, for addressing a specific service delivery. Meanwhile, the virtualization is somehow similar, but it implies the substitution of typical network appliances. Let's think, for example, of a firewall or a load balancer with a generic server where a software is processing the same function. Again, in this case, the advantage is essentially to have a higher flexibility, since the update of a firewall will not be just the substitution of the physical device, but just an update, updating the software itself, and also reducing the cost both in operation and investment, and moreover to be able to make heterogeneous appliances more easily convergent. And then I brought an example of what it is possible to do with the concept of virtualization and softwareization in cellular communication. Let's consider the example of a base station, which again, exactly as the router, can be divided into two main modules, which are the baseband processing, which performs the coding, the modulation of the signal, and the processing of the protocol. Let's think about the LTE protocol, for example, and the radio head module, which performs essentially the frequency filtering and the power amplification. So with the concept of virtualization and softwareization, we have seen that it is possible to move the baseband processing to a remote server or up to a remote cloud. What is the advantage of this approach? For example, we can operate different cells in an integrated way. We can coordinate the behavior of each cell and, for example, dedicate more resources to the cell where there is higher traffic. Or, for example, it is possible to coordinate them in order to reduce the interferences between the different cells. But we can do even more. For example, since the protocol processing is running on a common off-the-shelf server, it is also possible with the same server in an integrated way to process different protocols, for example, GSM and Wi-Fi, and for example, to dedicate some frequencies of GSM, for example, since it is not heavily used, to LTE, where there is a high demand of capacity. Or, for example, the single-use equipment can contemporarily connect to different radio access technologies in order to increase the reliability of the connection to the 5G ecosystem. So, in conclusion, we have seen how essentially the 5G consists on the virtualization of the network. Each of these virtual networks, which are go with the name of network slices, can be addressing specific use cases and can be reciprocally isolated. So in this slide, you can see that we have a generic, let's say 5G platform, where there are different users that are connected to the same physical infrastructure. But each of these users have specific requirements, since we have seen that we may have enhanced mobile broadband or, for example, mission critical service users. And we can observe how, although the physical infrastructure is the same, each network slice is configured differently. We have seen that, for example, the mission critical service users have strict requirements in terms of latencies, so many data processing modules can be hosted in the edge cloud. Meanwhile, we have seen that Internet of Things users have not the same strict requirements in terms of latency, so many modules in the data processing can be hosted in a remote cloud. So this approach makes the system much more flexible and much more optimal exploitation of the resources that are specifically addressing a specific use case. So this is the main concept of network slicing in 5G. And I have thought that it could be interesting to see some examples related to the smart grid scenario. For example, we may have a specific slice that specifically address feeder automation and protection communication. We know that in this case it is very important to have low latency and high reliability in the communication. Meanwhile, some other performances in terms of high bandwidth or high mobility are not that important. So a specific network slice may be addressing just this use case. Meanwhile, for other use cases like smart meters acquisition and load control, so in this case, mainly the monitoring and control of smart loads, in this case, a different slice can be established that have more relaxed requirements in terms of latency and availability, since we expect that the information stream in the case of smart meters will not be a continuous stream. And for example, in this case, at the moment, the smart meters have a time step of 15 up to 1 hour, 15 minutes up to 1 hour, so the latency may not be that important, but an important requirement will be in terms of connection density, since each home may have one or more sensors that do both monitoring and load control of smart appliances. Again, another slice for distributed generation control and also video surveillance. In this case, many studies propose the usage of autonomous drones for the surveillance of the power plants, like overhead power lines, the vegetation around the line, in order to do some planning in the maintenance. In this case, high requirements, of course, in terms of mobility, in order to allow a good a good performance when switching from one cell to the other, and also bandwidth, since some real-time video streaming can be transmitted to the control center. Finally, availability. In conclusion, the smart grid communication may be considered as a set of slices that address specific use cases. We can observe, for example, the difference between a smart meter slice compared with a protection slice. In this case, since we have seen how the latency is a very strict requirement, the data processing may be hosted in a fog cloud, so in a close proximity with the radio access points, in order to reduce the latency in the communication between breakers and control center, or between breaker and sensors. Meanwhile, in the case of the smart meter, since the latency is not an important requirement, the same data processing unit may be hosted in a remote cloud. In the last part of this presentation, I wanted to point out some issues related to the risk and reliability. Since we have seen how the inclusion of ICT potentially improves the capacity of operating the distribution network, but we know that the ICT at the same time both increases the complexity of the power system, and which opens to potentially new vulnerabilities in the power system seen as a complex system. So as a cyber physical system, the cyber part, the ICT, the power, and the physical system, the power system, which are interdependent and interconnected. And so with the ICT, we are addressing many frequent events like the monitoring of the system, the control for voltage regulation or overload management. So all of these are frequent events that, taken singularly, have a very moderately small consequence in terms of power system stability. But the introduction of ICT potentially opens to some rare events, so some small vulnerabilities that are, for example, bugs in the software or potentially malicious attacks, where the consequences may be very high. So for this, the invitation to rethink the methodologies that address the reliability of the power system and the risk assessment of the power system. In this context, me and my colleagues in the Department of Information Security and Communication Technologies are proposing a new methodology where the power grid and the ICT system are analyzed in the same simulation platform. In this case, we are using this software which is called Mobius, which is a software for discrete event simulation, typically for dependability analysis and performances evaluation, which we have extended with the power system libraries in order to analyze the reliability of the cyber physical system in an integrated way. So we have modeled a 5G system. Specifically, we are addressing the monitoring of the power system. So we have different measurement units which are connected to a 5G platform, where in a core cloud there is a state estimation which performs the state estimation of the power system. And what we could see with this simulation is essentially, first, appreciate what is the contribution to the unavailability of each part of the monitoring system: sensors, radio link, node B, so the base stations, and finally the cloud. And what is the impact of each of these subsystems to the whole performance of the state estimation algorithm in terms of estimation error and safety, both at a systemic level and also at a bus level for this specific network. And what it is interesting to observe is how, given the initial accuracy of the state estimation algorithm, which of course is brings to some error due to the inherent inaccuracy of the algorithm. This inaccuracy is amplified by the potential failure in the ICT system. So it is important when designing a new algorithm, both in the monitoring of the system, in the control or in the protection, to analyze what is the impact of communication delays or communication failures in the performances of this algorithm. And further work is in progress in my department also for analyzing not only the monitoring of the system, but also protection and control. So in conclusion, the two main messages that I wanted to convey with this presentation is to present 5G uh, and to show how it is a promising technology for supporting smart grid communication, since as we have seen, there is a quite large set of new technologies that promise to help in building a flexible communication network and specifically to provide quality of service level for many smart grid operation activities. And finally, uh, how it is important to consider the increased complexity and potentially severity of failure. So how our research investigation in this area, it is important in order to take into account the interdependencies between power system and ICT in the smart grid domain. This was my last slide. Thank you for your attention.